I finally get to talk about IP version 6. I'm so excited because since I've been teaching, which has been 11 years now, I've always been saying, oh, yeah, IP version 6, it'll come someday. Oh, yeah, it's always a topic that people want to just know about. And finally, I can say, yes, it's coming for sure. It's going to happen. So we'll start things off by talking about will we ever need to upgrade to IP version 6? And I guess I've kind of exploded that answer already. Yes, well, I won't say we will need to, but we're going to anyway. And I'll talk about when and why. We'll look at the format for IP addresses, what an IP version 6 address looks like. It's very different. We'll look at the headers and address types and also the types of communication we have in IP version 6. Like I've mentioned before already, that there is no such thing as a broadcast in this version. And then we'll go into an in-depth exploration. You will want to know what these addresses are all about. You'll want to know what the address types are, what they look like, just to get familiar with them because it won't be long before you're typing in that command on the Cisco router that assigns an IP version 6 address to an interface. Are we out of public internet addresses right now? I mean, think about it. In the world of IP addresses on the internet, do you think that we're really out of public IPs? The answer is sort of. We're first going to get into the rationale for IP version 6, which is a largely political and debated topic when you come to the technology field. It's kind of funny to see a political topic in the world of technology, but this is it. IP version 6 has been out for quite some time. I'd say we're approaching nearly a decade plus that it's been widely available for everybody to use, and in nearly 2 decades of testing and so on. And I still remember back in my early Microsoft days, I was teaching Internet Information Server 3.0. And I was talking to people and I said, I have a prediction. I think that the internet will be fully IP version 6 by the year 2003. And I missed it, obviously. But here today, we're still waiting. We're still sitting there saying, is the internet ever going to go to IP version 6? The answer is yes, and the answer is soon. But we have to first have a business rationale. So here is a list of the non-political topics of IP version 6, kind of the truth behind the matter when we look at some of the largely debated things. I'll stop talking about it. Let me get into this. First off, there is an IP address shortage. Not so in the United States of America. We are still sitting pretty. If you look at the public IP breakdown, we still have hundreds of millions of public IP addresses that are still unused and still available for people to use. So you might be thinking, well, why move? Why jump to the IP version 6 if there's that many really available? Well, it's primarily because of other countries. Since the United States was the one who developed the internet and created it, they control the IP addresses. And originally, now this is not true today, but originally Asia and Africa, the entire country, received two Class C blocks. Two blocks of 254 addresses for the whole country. Now, it has moved and they have gotten more today, but still, there's a huge shortage overseas. And because of that, they are actually far ahead of the United States in implementing IP version 6. They have many companies already running IP version 6 everywhere because of that shortage. So, there is an IP address shortage. It is being felt worldwide. Now, the current IP addresses are poorly allocated, meaning that agencies back in the day when the internet was first emerging would say, well, we only need a Class C, but let's ask for a Class B just in case. And they got it. The IP addresses, back in the day, we thought, why would we ever run out? So we just handed them out free for all. And it wasn't until a shortage was really being noticed that we started doing something about it and clamping down on who would get the IP addresses, but by then it was too late. I was amazed. I was actually teaching a class in a classroom setting, and somebody came in and brought in, they actually worked, I think it was for the University of Utah. I can't remember which university it was, but they came in and they said, check this out. And they gave me their IP address allocation, meaning what IP addresses they had, public internet address, and where they were being used. And I looked at it, I thought, no way, you've got to be kidding me. He had at least 10 Class B blocks of IP addresses that were untouched. They weren't even being used at all. They were just sitting on them. And I said, "Are you kidding me? What are you doing with these?" He's like, "I don't know. We have them because we were originally participating in the original ARPANET, and we just got these and have decided never to really give them out. And so there they are." And so that's what I'm talking about with poorly allocated IP addresses. There are Class B blocks where people are just still sitting on them because they don't know what else to do with them. And the exhaustion of the IP version 4 pool is hugely debated. Some people have said, some people have said that it would exhaust in the past. Some people have said, beginning 2009, we're going to be running out. Some people stretch it out to 2041 that we'll actually use the whole pool. Either way, we are moving to IP version 6. Now, I'll kind of pause right there in the middle. The move has begun. The Department of Defense of the United States of America has said that by the year 2008, their networks will largely be running IP version 6. Now, that's taking the government at its word that they're going to follow through with that date, but when you set a date like that, usually it's going to happen very soon. So, why move to IP version 6? New network devices on the rise, tons of them. I would say the large one right now that's really changing things is cell phones. And by the way, I don't know if you've seen this thing, but wow, I'll take one of these for Christmas. The iPhone is just an example of the new devices that are out there. You've got this phone that is a pure data device. It can do just about anything, web browsing and so on. And there's many other phones. That one's just Apple's pretty version. The Trio, the BlackBerry, some people call it the Crackberry. All of these phones that just are live on the internet and need public IP addresses. Those are huge on the rise. You're seeing new technology in every area of life. Refrigerators that have IP addresses. It's, crazy stuff. But nonetheless, you can see the next bullet. NAT, which is our current solution for the shortage, is now seen as a hindrance to innovation. You know what NAT is, network address translation. We've seen it for years, and I still think it's one of the coolest topics to talk about just because of how neat it is to set up. But people look at that now as not a neat, cool thing, but as something that is keeping IP version 6 from really hitting the market. If you can share 100 sorry, if 100 people can share one public address, or 1,000 people can share one public address with NAT, then why do we really need to move to IP version 6? So that's where a lot of businesses have hit the wall. They're like, give me a business reason. Give me a monetary reason. How is this going to benefit our business and grow our company more to move? And I will say, to this day, we still don't know. Meaning there still is not like a silver bullet that is going to drive IP version 6 in the business market because there's no killer feature. There's no major reason why to move. So what's probably going to happen is you're going to see the future features. You see the last bullet there. Potential future features. First off, IP version 6 in the RFC standard requires IPsec or encryption all the time, everywhere, to where there will be no more packet sniffers that are able to see network traffic that's going out without some sort of IPsec universal key that allows them to unlock that traffic. Mobility is a huge thing that IP version 6 can do that still IP version 4 has trouble. When somebody roams between routers, like wireless devices, mobility, that's what I'm talking about. IP version 6 has a simpler header, but again, all of those are cool, but not business motivators. So as I was saying, that businesses will probably either be forced into it, meaning the whole internet becomes IP version 6 and people are finally like, well, they're all doing it, I guess we should do it too. And it just becomes one of those kind of moves. Or it will be some killer future feature comes out where people say, wow, we need IP version 6 because of ... fill in the blank. So let's start with the number one motivator to move the internet to IP version 6. That is the sheer number of addresses. We've moved the address size from a 32-bit address in IP version 4 to a 128-bit address in IP version 6. I wrote down just how many addresses that provides. I'm not going to read that number to you because I don't know how to read that number to you. It's insane. It's a large number of addresses. Now, I know seeing that number on the screen makes you think, well, that's a big number, but we could still run out, right? Well, I want to read you something that puts it in perspective. Listen to this. There are currently 130 million people born each year, right? If this number of births remains the same until the sun burns out in 5 billion years, and all of those people live to be 72 years old, they can have 53 times the address space of the IP version 4 internet for every second of their lives. And we still will not run out 5 billion years from now. Tell me that's not insane. That kind of puts that number into a perspective to me where I'm just thinking, wow, obviously the IETF is not being frugal. They are saying this is something that will last us for quite some time. But here I am, in the year 2000, what are we? 2000. I don't even know what year it is. 2007? 2007. I'm standing here saying we will never run out. But you know what? I bet you, 50 years from now, some guy is going to be looking back and say, that Jeremy, he predicted we would never run out. Or, obviously, they're not going to be quoting my name 50 years from now. But they're going to be saying, oh, we predicted that we would never run out. And here we are. It's kind of like Bill Gates saying, we will never need more than 640K of memory. And here we are. So the point is that we can look at that number. I can read you a statistic like that. Although reading that statistic, even for me, I'm thinking we'll never run out. But who knows what the future holds. Now, to make addresses manageable, you can see with that sheer number of addresses, there has to be some way of dividing them and subdividing them. Just like we had network and host portions in the IP version 4 days, we are still doing that today with IP version 6. So the addresses, let me grab my pen here, are divided into 8 groups of 4 hexadecimal characters each. This is what an IP version 6 address looks like. Now, seeing that, it makes me think they better have a great version of DNS because I'm never remembering IP addresses off the top of my head anymore. But you can see, hexadecimal, we got 2001 colon 0050. The colons are like the dots were in IP version 4. Those are kind of like the octets. Each one of these hexadecimal characters, taking it back to binary because we will be working in binary, each hex characters takes 4 bits to create. So when you see like the number 2 in hex, there are actually 4 bits that are assigned to that. Each one of those, being the binary where we've got 1, 2, 4, 8, just like when we converted to decimal. And if you add all those up, the biggest number that you can get is 15. Okay, so in binary, essentially we have 0 through 15 possible for every hexadecimal digit. That's why we have in hex 0 through 9, and then A, B, C, D, E, F, right? As possible characters that we could have in our digits. Like you can see over here, we've got characters, A, B, C, D, E, F as possibilities in our IP addresses. So when you see these, and when you think of a 128-bit address, think of each one of these octets as being 4 bits, 4 bits, 4 bits, 4 bits. So we end up having a 16-bit octet rather than just the 8-bit that we had in the IP version 4 days. So that's what an address looks like. Now, to make it more manageable, we have 2 rules that help us shorten these IP addresses. First off, you can eliminate groups of consecutive zeros one time in the address. Look right here. You can see that the address has all zeros, all zeros, all zeros for 3 whole octets, and IP version 6 allows us to shorten those by putting a double colon. Now you can only use the double colon once in your IP address. You can't put 2 double colons because then the device will not know how many zeros go for each double colon. It won't be able to figure that out. So one time in our address, we can replace consecutive sets of zeros or consecutive octets of zeros with a double colon. Finally, rule number 2 says that we can drop leading zeros. So right here, some leading zeros, here some leading zeros, and we drop those out, and you can see that our address becomes at least a little more digestible. I'm not going to say it's short, but it's more easy to write or understand. Now, you cannot drop the following or succeeding zeros, so this 0 cannot be dropped. But that is a way that we can shorten the IP addresses to be more manageable. Anytime you have bigger addresses, you end up with a bigger header, and that's the case with IP version 6. Since the old addresses were only 32 bits in size, the headers fields, at least for those source and destination addresses, were only 32 bits each as well. So we are expanding how large each header is on the packet because of just the sheer size of those addresses. But the good news is we've actually simplified all the other fields. You can see that in IP version 4, we had quite a number of fields here that most of, without getting into the discussion of what each one of those are, most of them didn't really change or weren't used too often. So what they did was they went ahead and simplified them in the basic IP version 6 header to only contain exactly what was needed. The extra stuff is now added on through something called header extensions. You can actually, if you have proprietary applications or special needs, they'll add extensions to the header. Oop, down there. So you can tack pieces on, kind of like putting shims between the header and the actual data inside of the packet. The types of communication and addressing is where things really get different in IP version 6. Look at this. In blue is the types of communications, and we have unicast, multicast, and anycast. Now the good news is unicast is the same, one-to-one. If I want to send a message to you, I will send it to your IP address, and that is a unicast message. Multicast has become hugely important to IP version 6, whereas in IP version 4, it was kind of like, most people don't have it. Multicast is your one-to-many communication. This is going to be what replaces the broadcast. Remember I was talking earlier in the multicast video about the types of multicast addresses, the well-known ones, and there was one where you could send a multicast message to all multicast capable clients on the link. Well, that replaces a broadcast, and that's how we do broadcasts in IP version 6, but it goes further than that. Multicast can go just on the link. It can go to maybe just a local site of all the subnets at this location. It can go to an entire organization. It can go to the entire internet. There's many different scopes that the multicast has, and we'll look at those in just a minute. Now, the Anycast we had in IP version 4, but most people haven't heard of it. Anycast is a one to closest. If you've heard of HSRP, that's Cisco's redundancy, where you have one router that responds to the address unless it's down and then the other router takes over, it's kind of like an Anycast message, meaning you will assign multiple devices the same IP address. Now, there's no fancy gimmick with it. You just assign multiple IP addresses to the same devices, and that is then become an anycast address. So let's say you've got redundant servers, right? You want these two servers to back each other up, and you have replication going between them of all the files. Well, you could assign them the same IP address, and for the host, whichever server responds fastest, or whichever one the router finds the closest route to, that's why I have one to closest, that's going to be the server that is used. Imagine that in the IP version 6 internet, how easy it's going to be to configure, for instance, different web servers all over the world. There's nothing special that you have to do. Just give them all the same IP address, and the routers will find the best route to the one closest to them. And voila, you have immediate quote unquote load balancing around the world to where everybody's going to the server closest to them. That's the different types of addresses the communication that we have. Down here, we have the different type of addresses. I've got to admit, this is what threw me for a loop when I first got into IP version 6, because I always thought, hey, an address is an address, right? Not so. In IP version 6, your devices will always have, well, almost always have more than one IP address because we've got so many of them available to us. First off, a link local scope address is something that will allow them to reach their layer 2 domain. So when you think of layer 2 domain, think of just local subnet, their switch networks. We'll look at these in depth in just a moment, but I don't know if you remember the 169.254 addresses, or you've seen those before. Those are the ones that Windows or any device auto-generates when they find they can't get a DHCP address. And that is supposedly what allows them to communicate on the local subnet with other hosts. It's pretty much been a useless thing, because normally there's a major network problem and an outage when that happens, but that's what it was for. And that's what essentially the link local scope address does is just allow you to do local communication. Now, there was a large debate over this next type of address. Essentially, a lot of people didn't want it. They didn't want this unique or site scope address. They just wanted you to have a global address, meaning one that is valid on the internet. Like in IP version 6, I read you the statistic, right? We've got enough addresses to where every device in the world can have a public internet address, and most likely every device will. So with that in mind, we've got firewalls, we've got protection. Why do we need a quote unquote private address? Well, technically we don't, but our networks have been so geared around them in the past that people couldn't let it go. And I'm not saying I'm one of those people because I love private addressing. I love the comfort that I get by knowing I've got a NAT firewall and all of that. So that is what the unique site local scope address is. Now you might be wondering, why is it unique slash site? Well, it's because in two different RFCs, they renamed them. Meaning in the original RFC, they called it a unique scope address or a unique local scope address. And that became kind of confusing, and people were like, well, what does that mean? And then some people were like, well, we're doing away with this. We don't need this anymore. So they attempted to do away with it, and then in the next RFC that emerged to specify IP version 6 addresses, they said, oh, we're not doing away with it. It's going to be a site scope address. So the confusion in that, or it could be the other way around. Unique might be the newer one. Site might be the older one. We'll see that specific in a slide in a moment. Specifically in a slide in a moment. Sometimes I speak so fast all my words blur together. But this is what replaces the private addressing of yesteryear. This, as you might imagine, is what you will be using to communicate on the internet. And you can see my different ranges. Local scope, very small amount of devices. Site scope is within your organization. And then global scope addresses is to reach anything on the internet and be reached by the internet. That is a public internet address. Let's look at those addresses in detail, starting off with the link local address. This is the one that's auto-generated, just like the PCs nowadays that can't find a DHCP server, and they auto-generate that 169.254 address. But the difference is this is auto-generated regardless of DHCP server or not. Every device will have a link local address. Now, this is where we get into a little of the technicalities of our IP addressing. The RFC has specified that these addresses will always begin with FE80. Now, that is because the first 10 bits must be 1111, 111010. Now, when I got into IP version 6 addressing, I needed a little hexadecimal review. Just because I'm so used to decimal and binary from IP version 4, moving into the hex world was a little tough. But the first thing you have to remember is that every single one of these digits are represented by 4 binary bits. 1, 2, 3, 4. Now, the way it works is very similar to decimal. You have every character in the address has 4 bits. All zeros is really 0. 0001 is really 1. 0010 is 2. We all know this. This is basic binary. And you can keep going with that all the way up to just 9. You know, that would be 1001 equals 9. Now, this is where the hexadecimal gets a little bit different because we also have up to 16 values. It's actually 0 through 15 that's possible with 4 bits. So when we go to 1010, which would typically be 10, we then go to an A. 1011 ends up being B. We keep going. 10, or actually, hang on. 1100 would end up being C, and so on. You'd have 1101 is D, 1110 is E, and then finally all ones is how we end up with the F. So when you see that the first 10 bits must be 1111 for the first bits, it means that we're going to have F as the first one. You can see the E because that's the second set of 4 bits. Now you might be wondering, well, how did you get 8 with only 2 bits? Well, remember that the RFC specifies that the first 10 bits must be this. However, every single character in hex requires 4 bits to take place. So we have 8 coming because it's 1, 0, and not specified here, but the others are going to be 0 to make up that character. Because these link local addresses always begin with these first 10 bits and are followed with 54 bits of 0. So you can assume that every single one of these characters is going to take 4 bits, and if you ever see 2 bits, well, we need 2 more to make a character, so that's where we get the 8 from. And of course, the 0 bops in because every IP version 6 address has 4 characters, 4 hexadecimal characters per octet separated by colon. So that's why we end up having that FE80. Technically speaking, most of the time you'll see it written FE8 in the RFC standards, but the 0 is what you'll always have on your address because of the following 54 bits of zeros. So that's our first octet. All of this right here, first 64 bits is what we just talked about. Now the last 64 bits is where it gets a little bit weird. Let me clear this off here. The last 64 bits is the 48-bit MAC address from the host, whatever host this is being generated on, followed by, or I should say, squished between FFFE, or that is squeezed in the middle. It's hard to say that because here's the idea. Let's say we've got a host with this MAC address. Well, that's 48 bits, but we need 64 to complete the 128-bit IP address. So what the last 64 bits will be is first 4 of the MAC address, 0019, 0019. Second 2, D1, D1. And then for some reason, the designers and the powers that be decided to squeeze FFFE right in the middle. So in every single link local address, you'll always see the MAC address with this kind of sandwiched between the two ends. And then you can see the rest of the MAC address, 2222, DCF3, DCF3. So that will end up comprising the last 64 bits of that IP address that is only used for link local communication. Now, it doesn't have to be used. For instance, if you had other IP addresses that were being used to communicate outside, those would be used. But if you're speaking to somebody on the same link and you realize that you have a source address coming from that link, then you can use your link local address to communicate with them. Now let's move into the second debated IP address type, the unique local or site local addresses. I think I mentioned this backwards before and corrected myself. Unique local is the new name. RFC 4193. Site local is the old name that was in RFC 3513. So we're supposed to be calling these unique local addresses, which I actually like the old name better, site local, because it really describes what they do. They are used within enterprise networks to identify the boundary of their networks. So you can expect that these addresses will be relatable to the private addresses of IP version 4, the 10 range, 192.168, all of that. This is kind of the same thing. Now, as it is specified in the RFC, they will use the following format. You can see that the first 7 bits must be all ones for the first one, that's our F. You can see C as the second one, and then 00, but the RFC specifies that only those 7 bits must be that way. So that's why we have 1, 1, so there's 4 bits there, 5, 6, 7. The RFC mentions that this last bit right here, the one with the L, is going to be up to you. But it's kind of funny because they say all locally assigned addresses, meaning assigned by you, you should set the L to 1. So our real first 8 bits are typically going to be 1111, 1101. 0 is currently reserved for future use by setting that L to 0. So currently, the site addresses will all begin with FD00 colon 8 because even though the RFC says only the first 7 bits have to be set, they say, oh yeah, by the way, that last little L bit on the end should be set to 1, which means it's locally assigned by an administrator, thus making all enterprise addresses or all private, I guess you could say, IP version 6 address starting with FD00/8. Now, it seems funny when you look at something like that to be like, oh no, you're locking it down. There's not enough private IP addresses. But remember, we've got 7 full octets. of 4 hexadecimals each that I mean that's a cajillion different IP addresses that you could use within your organization. And likewise, that's why they split up these separate sections. You have 40 bits which represent the global ID. That's intended to be your company. Like everybody in your company will have the same 40 bits starting their IP address, or I should say following the FD00. The next 16 bits here are going to be the subnet ID because you're going to have VLANs, you're going to have subnets within your company's WAN links and so on. So this will identify the specific subnets. And then finally, the last 64 bits, just as we saw with the link local address, will be the interface ID. It'll be spliced into a MAC address style format like the other one was, or you could come up with your own interface ID depending on the host that you're working with. It could be a DHCP pool. There is DHCP version 6. Whatever way you're assigning interface IDs, that is what this one will be, and that will result in a globally unique, at least within your enterprise, IP version 6 address. So we've seen the unique local addresses or site local. We've seen the link local. Next up is the global, not so local addresses. These are going to be the new pool of IP addresses that will build the IP version 6 internet. As of right now, the only thing the standard will say is that they have to have their first 3 bits, high level 3 bits, set to 001. And what that comes out to be is 2 000 or 2 something colon colon 3. You can just see the first 3 bits are what make that number 2 show up, but everything else is fair game. Now you can see the global routing prefix. This address is divided into 3 major sections. The global routing prefix is 48 bits or less. It could be smaller, could be larger. The subnet ID is going to be comprised of whatever bits are left over after you have this global routing prefix. Here's the idea that the powers that be have decided on for the internet addresses. We've got this pool starting with 2XXX. Anything after that is fair game. So we can go ahead and assign, maybe 2 000 colon 0, da 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 da, some up to 48 bits right here for this global routing, and that'll go to Asia. And 2, da 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 down the line, that'll go to Egypt. Where did that come from? Egypt. How about like Australia or Egypt? Why not? Or these will go to Iran. These will go to Canada. You get the idea. They're going to be chopping these up into giganto blocks and assigning them to the nations, which they already have done. Many assignments have already been made. You can look at the RFC and they'll show you, who's got what blocks. All these different unions have been assigned different blocks. But the primary addresses expected to comprise the IP version 6 internet are these. The ones that are coming from 2001 colon colon slash 16 subnet. That is the IANA's block, and that is their range that they've chosen to use and start assigning. So you're going to see ISPs everywhere start getting blocks of those. As a matter of fact, you probably are able to go and apply for your own block right now. Who knows? Maybe you'll be one of the early comers to the IP version 6 address space, and like 20 years from now, you'll be looking back saying, I'm glad I got that block. Who would have known we'd run out? Who knows? But that's how they splice up all of those different global addresses, and those will be public on the internet. The last type of address that we're going to talk about in IP version 6 is the multicast address. This one is huge in IP version 6, as we've said many times, because and when I say we've said, I mean I've said, because I'm kind of schizophrenic. But the multicast address is what we're going to use for any kind of group communication, even the old broadcast style. Now, the way it's engineered is that the first 8 bits of the multicast address are always all ones, which means multicast address starts with FF. That'll be your signal that you're looking at a multicast address. After that, it's kind of cool. They've divided up into 3 major sections: the flag bits, the scope, and the address. Now the flag is it gets a little deep. It's 4 bits long. It's only 4 bits. And every single bit means something. You can see that this is the 4 bits spelled out. We've got the 0, which actually is the only bit that doesn't mean something because it's not being used yet. It's an unassigned bit. But you can see right next to that is whether or not you're using a rendezvous point. Next to that is whether or not this address is based on a unicast address. You can actually use unicast addresses to create multicast. And then the last one, the last bit right here, is whether or not, and this is one you want to know, it is a permanently assigned address, which would be a 0, or a not permanently assigned or temporary address, which is a 1. There are some well-known multicast addresses, which the IANA has assigned, and they say you don't touch these. These are things like the way RIP routers communicate or OSPF routers. These are well-known and not touchable, so they would have that T-bit set to a 0. But the ones you can make up for your own internal broadcasts or maybe a broadcast segment, you know, now called multicast segment, would be a 1 because it's locally assigned, you are in control. Then the next set of 4 bits is going to define the scope. This is what I think is pretty neat. Depending on what you set, it's 4 bits, so just one hexadecimal digit. Whatever you set there will define how far the multicast goes. You can see it, interface means it doesn't even leave the local computer. The link means it's, to the local subnet around you, so that would be your local switch segment. You have the subnet, which is where you can start reaching other subnets. Link local means this is just the local link, and you can reach what's out there, which could be your subnet. 3 is to a subnet, which could be yours, it could be other subnets. You have the admin scope, where an administrator can define specially defined ranges. The whole site, an entire organization, there's different levels that this thing can reach, all the way down to the global range, which would be something that would go across the whole internet. Maybe it's a internet radio stream that anybody can subscribe to. So depending on what you have set in those 4 bits of the scope, is how far it will go. Finally, you have the actual address, which is everything left over after the 8 plus 4 plus 4. So that'd be after 16 bits initially. The rest is whatever you want it to be, the address, where you can go in and specify what the multicast address is, as long as you are not stepping on the ranges already reserved by the IANA. We'll see some of those right here. These addresses give me hope because I look at them and say, oh, I could remember that. It's not as bad as a huge IP v6 address. If you have the initial digits of FF02, immediately that tells you this is a multicast address. There's no flag set. That's the flag hex digit right there. And then this is the scope. 2 means the link or on the link. So when you send a message to FF02, colon 1, so everything else is zeros all the way up to the last one, which is 1. That is your way of reaching all nodes on the link. Can we say broadcast message? That is going to be the new style of broadcast that allows you to reach everybody. The second one, FF02, colon 2, is all multicast capable routers on the link. Is this ringing any bells? Do you remember when we talked about multicast specifically? We had 224.0.0.1, which is all systems, 224.0.0.2, which was all routers on the link, 224.0.0.9, which was all RIP routers, or 224.0.0.5 and 6, which was OSPF and OSPF period. So they've replicated or used the same strategy of those multicast addresses. It's just with an IP version 6 slant on them because they're IP version 6 addresses. So look at this one. This is your new style of ARP message. FF02 colon 1, so a bunch of zeros, 1, and then the last 2 octets of the addresses are FFXXXXXX. This is a new style of ARP message. First off, you can see right here that this is designed to go to all systems on the network. From there, the FFXXXXXX is requesting information for whoever has an IP address where the last 6 digits are this. And you would see, and if you were doing a packet sniffer, if it wasn't encrypted, you would be able to see that this is going to be the last actual 6 digits of an IP version 6 address that it's asking for. Now you might be thinking, well, isn't there a chance that another system on that network or on that link would have the same last 6 digits. And I would say the chances are really, really, really slim, but they are there. There is a chance that you could have some device that has duplicate the last 6 digits right there. So what happens? Well, an ARP message isn't just carrying this request. It has a payload. This is just in the header. This is the destination address it's being sent to. Behind that is a payload which has the full IP address, IP version 6 address it's looking for. So while both systems would receive it and process it, only one of them would respond, and that would be the one who really has that full address that's listed in the payload. So even the ARP message gets a little more sophisticated when we get to IP version 6, and that would be looking for what layer 2 address that IPv6 device has. Now, the last one you see on the list is FF05::101. I just wanted to give you another example that was not an on link, meaning FF02 as the scope. You could have this to go to all NTP servers, that's the well-known multicast address to reach them, within the site. So that would be a multicast message that could reach all NTP servers in your organization. Maybe you have a master clock, master NTP clock on the network that sets the time on all the other NTP servers. How efficient is that? To where it can just send a multicast message to the whole organization that only the NTP servers will receive that says, hey guys, this is the current time update. So all the clocks can be synced all at once. I mean, that could even go to all clients, all servers, however far you wanted that scope to go, that allows them to receive the time and automatically synchronize their clocks to the main NTP server. This stuff is cool. So that should give you a pretty good idea of what you're looking at in the IP version 6 world. Now, the good news of all of this is that in the command to assign an IP address to an interface, Cisco has finally allowed you to use bit notation for the decimal subnet mask or for the subnet mask of these IP addresses because there is no decimal one. I think I've gotten more emails about that question than anything else, where when you go under an interface and you type an IP address and the IP address, you can't use /24. You have to type in the decimal subnet mask. Now everybody wants to know, when will Cisco fix that? And they finally did because there was no other option. So what we hit as we went through this was the business reasoning, or I should just say general reasoning, for upgrading to IP version 6. Yes, we will need to. Yes, it will happen. It's just a matter of time, and it will be a matter of time for the businesses to catch up. I also encourage you to check out the upcoming video where I start talking about how businesses will make that transition into IP version 6. Really good stuff. So then we looked at the IP addressing format, where the general format of what an IP version 6 address looks like and the ways of shortening it. We looked at the address headers and address types and even the communication types tied into that. And then finally, we did an in-depth exploration of the new addresses, ranging from the link local to the unique local to the global, and then finally the multicast address. I hope this has been informative for you, and I'd like to thank you for viewing.